And the difference is that the kube control rolling update the replication controller on the client side. So it will, if you have a replication controller and you want to update its part template, like you want to update the image, and then you'll use that to give it like scale up to the new part template one at a time, and scale down the old template one at a time, and you do that rolling update. And then with deployment, you can do that in server side, and you get more customization from the deployment spec. So what deployment does is that it creates replica set, and replica set, you can think of that as a next generation replication controller. It just has different selector than replication controller. So replication controller only has the equality-based selector, but the replica set has set-based selector. So that's the main difference, but you basically can think of them as the same. And then, so deployment will create, once you create a deployment, you will create replica set, and if you update the part template of the deployment, you will scale up the new replica set and scale down the old one. So I'll show you a demo to see how that actually works. So can you guys see my screen? Okay. So I now have a local cluster running, and then I use a website to visualize what's happening. So at first I want to start a deployment, and I can use create-f to create a deployment, or I can use run to easily create a deployment. So I create a deployment named update demo, and its image is this image. And I want to export to port 80, and I give it some label. So once I hit enter, it'll create a deployment called update demo. And here you see there is a running pod created by the deployment. And if you do the kube control get replica set, abbreviated as RS, you can see it creates a replica set with the same name as the deployment, and then some hash of its part template as its name. So then I have this deployment running, and I want to scale it up to 4 replicas. Then you can see it gets scaled up, everything is running, okay. Then let's say I want to update the image to the next version. Let's say I want to update the image to Kitten instead of Nautilus. Then image, I can use this kube control set image to quickly change the image of the deployment, the image of the part template of the deployment. It's a new feature. So I set the image to this. to this kitty image. And you can see the image is updated, but then you can see there's 3 Nautilus running and there are 2 pending. Why is that? Let us get the pause to see what's happening. So as you can see, there's image pull back off. And if I describe this part, this part who's failing, I can see that there's no kitty image. So I say, okay, I need some time to figure out what's going on. Let me roll back first. So the way we do rollback is roll undo. So you can undo the rollout you just did. Undo this deployment rollout. Then it's rolled back. Everything is back to normal. And then after some time, I figured that, actually the image that I want to use is kitten. So I change it to kitten. You can see it's scaling up the new one by one, and scaling down the old one by one. And finally, it's all done. You want to see if it's all done, you can also do the rollout status deployment. It will tell you it's successfully rolled out. And if it's still in progress, it will also tell you, using a watch to tell you what you're waiting for. So that's basically it.
Any questions for Janet?
Yeah.
Yeah, I have a question. About the kubectl rollout status, how is that queried on the server side? Is it just a watch on a specific status for the replica set or the deployment model itself?
Yeah, it's looking at the deployment. There's a deployment generation and observed generation. You compare the deployment generation with the observed generation, you can see if the deployment controller has seen the change. What that means is that if the deployment controller sees the change you made to the pod template of the deployment, and if that match or the observed generation is greater than the generation, then everything is fine. Then you can look at the deployment. Let me show you its okay. Let me show you its config. So you can see there's a generation and there's a observed generation, and you can see it's nice. So that means the controller has seen this update, and then I can see the updated replicas, which means the replicas of the new replica set you have. So if this matches the spec dot replicas, that means you have all the new replicas up. And this one is for the available replicas. So available means that you can set, there's a field that you can set called min ready seconds. Where is that? Okay, there should be a field called min ready seconds.
I think it's a mid empty.
Oh yeah. So if it's empty, that means you don't wait after a pod is ready. You don't wait for anything. You just assume you just think it's available. But if you set the min ready seconds, you can set it to like 5 seconds, 10 seconds, and the pod will be considered available only after it's ready and it's passed ready for the min ready seconds. And the deployment will use the available replicas to scale up and down the do the rolling update. I mean, so I can say I want at least 4 replicas be ready until I can scale down, things like that.
Cool. Thank you very much.
Awesome, thanks. Who else has questions for Janet? Okay, if there are no other questions, we're going to move on. Thank you so much for a fantastic demo, Janet.
Yeah, no problem.
Okay, and up next is Saad.
All right, thank you, Michelle. Thank you, Janet. I'm going to talk about Kubernetes storage. It's going to be a very basic overview, so some of you may already be familiar with this content, but it's just an introduction. Let me share my screen. All right, so my name is Saad Ali. I'm a software engineer at Google. I work on Kubernetes storage. So one of the problems with containers is the fact that the files inside the containers are ephemeral. When a container crashes or when it completes normally, all the files in the container, once the container is terminated, are lost. So that means you can't really run a stateful application in a container alone. And that, combined with the fact that you can't really share files between containers very easily, really sucks if you're trying to run a stateful application. And so the solution for that in the Kubernetes world is Kubernetes volumes. The idea with Kubernetes volumes is pretty straightforward. We basically mount a directory with some sort of data into it, into the container, and we make it available to all the containers in a particular pod. And unlike Docker volumes, the lifetime of these volumes is essentially the same as the lifetime of the actual pod, or in some cases it'll outlive the lifetime of a particular pod. And the details of how individual plugins are implemented varies. How the directories are set up, the medium that backs them, the contents of the directory, etc., all depend on the type of volume plugin. There's a link there where you could start reading up on volumes if you'd like. And so we've got tons of different volumes, I think 15 to 20 right now. There are ephemeral volumes like empty dir, secrets, config maps, downward API. These are volumes that are created when a pod is created and then torn down after the pod is killed. And then you have network attached storage, things like GCPDs, Amazon Amazon EBS. We even support Azure now, NFS, of course. And those allow data to persist beyond just the life cycle of a particular pod. So very quickly, I'm going to walk through a demo. Unlike Janet, I'm not going to do a live demo. I'm just going to have a pre-scripted demo that I've stepped through. This is to demonstrate empty dir. Empty dir allows us to basically have a directory that's shared between multiple containers inside of a pod. It's a temporary directory. It's created and it's empty when the pod is created. It's shared between all the containers. All the containers can read and write from it. And when the pod dies, the directory and its contents are then deleted. So over here we have a basic replication controller with a pod definition. We define one particular volume, an empty dir, for use by this pod. We're going to call it data, and it's just a simple empty dir. And we have 2 containers in this pod. We're calling them Sleepy Container 1 and Sleepy Container 2. They basically just wake up, they've got a busy box image, and they go to sleep. And both of them are mounting that data volume, which is an empty dir, into a path/data. And so now if we go ahead and we create this, this particular replication controller on our Kubernetes cluster, we're going to see that the 2 containers are up and running. And then what we can do is basically log into the first container and take a look around. If we do ls, we see that data directory there. And if we ls the data directory, we see there's no content in the data directory initially because we haven't written anything yet. And so from that first container, we can go ahead and write something into the data container. In this case, we're just going to echo hello world into the data container, into a test file. And we'll exit from that container. And then if we log into the second container, sleepy container 2, and we ls data, we see that the file that we wrote from the first container, test.txt, already exists because that particular directory is shared between the 2 containers. And then if we echo the contents of that, we can see what we wrote. Moving on, so that empty dirs are great for just sharing data between 2 different containers. But in order to run a real stateful application, you need to be able to persist data beyond the lifecycle of a single pod. And that's where network attached storage comes in. And we've got a bunch of different network attached storage plugins, GCE-PDs, Amazon AWS, NFS, a whole bunch of them. So I'm going to step through an example using GCE-PDs. In the end, the containers, just like empty dir, will have a directory that's mounted, that's shared between all the containers. The only difference is that after the pod is terminated, this directory is not deleted, it's simply unmounted, and then the underlying disk can be reattached to a different node and be available for a different pod. So to walk through this example, we've got another replication controller. This time I am going to specify the node name so that I can force it to land on a particular node. And the idea here is going to be that I'm going to create a container on a specific node. It's going to have a GCE-PD attached to it. We're going to write to that GCE-PD. Then we're going to go ahead and delete that pod. And we're going to reschedule it to another node and recreate the same pod. And we're going to see that the data that we wrote initially still exists because it was persisted on the disk. So in this case, again, we've got a single container, sleepy container. It's a busy box. It wakes up, or it starts up and it goes to sleep. And the volume in this case, instead of an empty dir, is a GCE persistent disk. It's backed by a GCE persistent disk called Panda disk, and the file system that's on it is ext4. The interesting thing with GCE PDs and a lot of these network attached storage devices is that we detect if the volume is not formatted, and we'll go ahead and format it automatically for you. So in this case, if this volume was unformatted, we would format it with ext4 on mount. And so inside the container, it's going to be mounted at the same path/data. So we go ahead and we create this replication controller against our Kubernetes cluster. Replication controller created. We can do get pods to see the actual pods. The containers are ready. There's one container and it's ready to go. That means that the underlying GCE PD was attached to this particular node. It was mounted into this container, and this container is now ready to go. So if we log into this container, we can look in the data directory and see that it's empty. Then we can go ahead and write some data into it and exit out of that. Then what we do is we go ahead and delete that container. When we delete that container, a bunch of cleanup routines happen. And in this case, for GCE PD, it ends up detaching that particular, unmounting and then detaching that volume from the node. And now we're going to go ahead and change the node name in our replication controller to a different node to force it to land on a different node, just for the sake of this demo. And now if we recreate this particular pod using this new replication controller with a new node, we get a new pod that landed on the second node. And after some time, it's going to become attached, and the volume is going to get mounted into the container again. So if we log into the container and we ls data, we can see the file that was written the first time around, and we can see that the data is still there. So basically, this is how you can create stateful applications on Kubernetes just by using network attached storage. And so those are a couple of ways to be able to directly specify the exact type of volume that you'd like to use. Another option is to use the persistent volume / persistent volume claim interface. The idea here is that there's an abstraction layer. Instead of having to specify every time that I want to use a particular GCPD or a particular NFS disk, you can have a pool of persistent volume objects that represent storage. And when as a user, you're ready to consume some piece of storage, instead of saying I want a particular one, you make a request for storage. You say I want this particular size with this particular access mode. So you create a persistent volume claim, and then that claim automatically gets matched with the existing persistent volumes and bound to it. And once it's bound, then you can go ahead and use that persistent volume claim as part of your pod definition. So we could step through an example of this very quickly. So in this case, we are defining two persistent volume objects, myPV1 and myPV2. These represent two different underlying GC persistent disks. One is called Panda disk, and the other is Panda disk 2. And they are different sizes. One is 10 gigs, and the other one is 100 gigs. Both of them permit read-write once. And so we can go ahead and create that persistent volume, these persistent volume objects in the Kubernetes cluster, and we can see that they immediately become available for use. Next up, we're going to create the persistent volume claim object. This is basically a request to say, I want some piece of storage. And in this case, I'm requesting 100 gigs and read-write once. So when I go ahead and create this persistent volume claim, what ends up happening under the covers is that it automatically gets matched with the existing 100 gig PV, and that becomes bound. And so now my persistent volume claim is bound to PV2. And from there on out, I can go ahead and use the persistent volume claim directly in my pod. So in this case, instead of specifying a particular disk directly, all I have to do is specify the name of the persistent volume claim, and Kubernetes takes care of doing the dereferencing to figure out what exactly the underlying storage is underneath. So that, in a nutshell, is volumes in Kubernetes. What's coming up? So we have a couple of alpha features that are pretty cool. Dynamic provisioning. So you noticed with the GCPD examples, for example, we had pre-provisioned disks. We assumed that Panda disk already existed. So with dynamic provisioning, we have the ability to provision volumes on demand. So instead of having to have a pre-existing pool of disks, we could basically create on demand a new volume with whatever parameters the user provides. This feature is in alpha as of 1.2. It's currently triggered by an annotation on the PVC object. So to use it, basically what you do is instead of creating a PV object, you're just going to create a new PVC object, basically a claim, and you're going to include this annotation. And Kubernetes automatically goes out and calls the correct provisioner to provision that piece of storage and create the PV object and bind it, and then you can use it exactly as a normal PVC object. This feature is, we anticipate that in 1.4 we're going to fully flesh it out into a full-fledged feature. So keep an eye out for that. For 1.3, we recently introduced pet sets. Pet sets allow for clustered applications. So oftentimes it's not sufficient to just have a single pod running with a single network attached storage device. In order to be able to scale out, in order to be able to do things like sharding, we need a stronger notion of identity. And we have things like replica sets, but replica sets are very much, they are a pet versus cattle, right? They are cattle. They have no notion of identity. So if you scale out a particular replica set, all the pods in that replica set are identical. Pet sets is a new concept which allows you to basically scale out a pod while keeping identity for the specific individuals of that set. And for storage, what that means is that as you scale out, you have a uniquely identified underlying volume that you can associate with each pod. And when that pod goes away, the new pod that comes up to replace it knows what the identity of the previous pod it's replacing and uses the same underlying storage. So that really allows for scalable clustered applications. And that's pretty much it. Does anybody have any questions?
Don't be shy. Thanks so much, Saad. Anybody have questions for Saad? I think you have a question in the chat.
Okay, let me pull that up.
Yeah, that might be better.
Yeah, I think that was, I misspoke. So Docker volumes have no notion of a lifetime. And so they are basically a directory on the host machine. There is no life cycle associated or controlled with the container itself. So it's exactly the opposite of what I mentioned. With Kubernetes volumes, you actually have the ability to have volumes that have life cycles that are controlled with the pod/container itself. So for example, we have the ability to, for example, secret volumes are a great example of this, where when a pod is created, you can have the secret API objects from your Kubernetes cluster automatically get populated into a directory in your volume, have that available for your containers, and then have that torn down after the pod is completed. And so that concept doesn't really exist in the Docker world. In the Docker world, all you have is a directory sitting on the host machine, and that's it. Any other questions?
I think we're good.
All right. Thank you, everyone.
Thank you. We are over time, but Matt Frainer, are you on, and do you have any updates on the survey?
I sure do. In fact, I was going to share what I found, but it'll take more than a minute or two. Should we hold it off till next time?
Yeah, let's hold it off till next time. We'll eagerly await those results. And I'm sure they'll be in a blog post later too. So, okay. Well, thank you everyone for joining. And I'll post the notes and recording from this meeting later today, as well as the agenda for next week is already up, but might change. So yeah, thanks Janet, thanks everybody for coming. Have a great day.
Thanks. Bye.
Take care.
Thanks, bye.